My name is Benno and I will talk about neutrino-induced reactions on carbon. But first I like to tell something, facts about neutrinos. What is a neutrino? Until today we don't have a real answer to this question. Wolfgang Pauli invented the neutrino to resolve the missing energy in the spectra of radioactive beta decays. At that time only the electron or positron of the beta plus or beta minus decay was detected and the recoil energy. So it was a one particle decay addressed. So the expectation was that it is a monoenergetic, that we should observe a monoenergetic electron or positron depending on the decay. So he invented third particle, a neutrino, which get all this missing energy to resolve this problem. And this was in 1930, and it was thought that this particle wouldn't be possible to detect. It took 26 years to discover the neutrino, which was done in reactor neutrino experiment by Rains and Cohen. They had a detector at a distance of 11 meters far from the reactor, and it was a 200-liter water tank filled with liquid scintillator for seeing the reaction of light and using photomultiplier tubes to see the reaction, and was dissolved cadmium 40 kilogram of cadmium chloride to see this reaction. The reaction signature is we have the electron antineutrino from the nuclear reactor, which does a reaction on the protons of the water, leading to a neutron and a positron. The positron gets the next electron nearby to do an annihilation. So the prompt signature of this reaction is to see two gamma quanta of 511 kiloelectron volts. The neutron then is thermalized and captured by the cadmium atoms, the cadmium 180. So it absorbs this neutron somehow to create cadmium 109, and leaving a photon which also can be observed. So the observation of these three gamma quanta was a signature to really detect these antineutrino reactions in this reaction. Okay, let me talk something about reaction cross-section. The reaction cross-section is somehow a differential equation. We have the flux of incident beam traversing the target of thickness dc will be reduced due to a reaction of the beam particles with the target material. So if you look at this equation, we do a separation of the variables. We can put the phi under the d phi and put the dz on the other side. So this d phi divided by phi is something like the number of incident particles which did the reaction divided by the total incoming particles of the measure of the experiment. So sigma is in the former experiment of Rains and Cohen in the order of 10 to the minus 44 square centimeters, which is a very low value. So in doing experiments where neutrinos are involved, we need a long measuring time, we need a very intensive neutrino flux, and we need a big detector where we have a lot of scattering centers to make such reactions probable to observe. And And now I like to say something, where are neutrinos involved? Well, all radioactivity is involved with a weak interaction and with neutrinos. Of course, reactor neutrinos I have told, but radioactivity is used in radiotherapy and medicine. We have geoneutrinos, we have the natural decay lines of uranium and thorium. We have dating methods with radioisotopes like carbon-14. Neutrinos play a role in astrophysics, like the solar neutrinos, like supernovae or star collapses, and active galactic nuclei. Neutrinos come in the cosmic rays. We see them in atmospheric neutrinos and or in high energy neutrinos flux from astrophysical objects like active galactic nuclei. In cosmology, we have a neutrino background radiation of about 1.9 Kelvin, which until now couldn't be detected. They play a role in matter-antimatter asymmetry in the beginning of the cosmos, and they also could be candidates of dark matter. And of course, a big amount of accelerator neutrino experiments which are involved. So all these investigations led to the theory we call now the standard model of particle physics, which is a theory of electroweak interactions and nuclear interactions. And I like to emphasize the part here. We have the 6 quarks, and of course the antiquarks, and the 6 leptons, the neutrinos, and the electron, the muon, and the tauron. What is important to see, the neutrinos in the standard model have 0 mass. This means the only difference between the neutrino and its antineutrino is the definite helicity that they have. So neutrinos only emerge as left-handed, and the antineutrino therefore is only right-handed. If they have no mass, then they are distinct. But we had experiments in the solar neutrino sector and the atmospheric neutrino sector. There have been emerged neutrino oscillation reactions, which are related that neutrinos, minimum 2 neutrinos, need to have a mass at rest. So it could be that the neutrino is its only antiparticle if we change the helicity. No? If it has mass, this can be done. And so until today, we don't have a clear picture of the neutrino, whether it's a Majorana particle or a Dirac particle. But oscillation experiments showed that we have a measure of the difference of the masses of the neutrino flavors. The only missing particle was the Higgs boson, which was discovered in 2012, which has a mass of 125 giga-electron volts, and this was the only particle which was missing in the standard model of the particle physics. So it's complete now, and we can turn things around. We can use the theory to do predictions and use this for predicting measurements. Let's come back to the isospin triplet, where I like to show neutrino reactions.
Okay, you have 2 minutes.
2 minutes, okay. If we neglect the differences in the Coulomb interaction of the nuclei, the energy levels are degenerates. So we can treat them as isospin states. And we have here a lot of reactions we can observe. We have the beta plus minus decay of carbon to the boron or to the nitrogen, or we can observe them in electron neutrino inelastic reactions. I like to make an example. If we think, for example, a pion decay at rest, there emerges a muon neutrino of 29.8 MeV. This can do an inelastic excitation to the carbon level 1+1. And if we adapt the selection rules of quantum mechanics, we see that this is somehow related with the flip of the angular momentum of 1 unit and the isospin of also of 1 unit. What is important, there is no parity change involved. So to describe these reactions, we need tensor operators, and due to the theory, which is vector and axial vector of type, we have the Coulomb, the longitudinal, transverse electric, and transversal magnetic operators, and they are distinct in the parity. They transform distinct with parity. For example, we had a spin flip of 1 unit, so the only operator which can emerge in the vector part is the transversal magnetic, because this leads the parity positive, and in the axial vector we have the contribution of M5, L5, and TL5 to describe this reaction. The flip of isospin of 1 unit and being in the carbon sector shows us that it is an isovector neutral current reaction. And so only Tmac, M5, L5, and TEL5 operators contribute, and these are the selection of delta J 1 and isospin 1. We can describe this in a particle hole description with particle wave functions. Below here we see the many particle multipole element, and it can be expanded a single particle wave with a sum and superposition of single particle wave functions with somehow transition probabilities, and can use the oscillator single particle description to describe these elements. We have to take into account 4 transitions, because the S shell and the magic numbers of the model give somehow stable configurations. So it is we need a lot of energy to excitate this of the 1s 1/2 orbital. So only in the p orbital we think there are contributions to the excitation. And so these 4 excitations have to be taken into account. When we do the calculus, we end up with this formula for this reaction, cross-section of this reaction. This can be simplified, so it is somehow a polynom of second Crow in the beta axial vector coupling constant, and with parameters, with real parameters in French. When we do these calculations, we end up with a theoretical Newton current cross-section of these muon neutrinos, and here you see the values of the theoretical prediction for this reaction. This means that if we have 1 neutrino coming into the detector, we need 2.7 carbon nuclei, 2.7 times 10 to the 42 carbon nuclei on the trace of this neutrino to observe 2.7 reactions. So the crucial point I like to figure out is that all observations with the neutrinos are related to the knowledge of neutrino-nuclear interactions. This shows the importance of these studies. And please let me make some outlook. There are a lot of unsolved questions about neutrinos. We have the theory with a lot of free parameters, and we don't know why we have 3 generations, why the interaction is of the type vector minus axial vector. We don't know something about the neutrino, whether it's Majorana or direct type. The CP violation in the early universe is a big question, and the dark matter candidates. And of course, we like to do unification with the gravitation. The calculation reference is here below. So thank you very much.
Great, thank you. Bom, passamos direto então para perguntas.